which I keep forgetting. There will be a Good Friday sometime in April, and there will be no class because it's on Friday, and I was told I have to make this announcement. Let's see. I guess it's probably April 10th. Yeah, we will not have a class. Is it in April? Okay, so anyway, it's a holiday and no class. Okay, so very good. So any questions to me? No. Hopefully, we're going to finish today conformal field theory, and I will have a new homework assignment for you. So this one will be much more difficult, but there will be only 3 problems. It will take you some time. So, how are you doing? Okay, so let's go back and recall where we ended, right? So if we have a conserved current, so conserved current has a holomorphic plot, right? And it has an anti-holomorphic plot. And so what we showed that once we have a conserved current, then we can construct conserved charges by simply evaluating a contour integral dz by I dz, and so that produced for us conserved charges. And then what we discussed extensively is that once we know these charges, so Q's, so this is conserved current, and so those are corresponding charges. And so one of the very important aspects that we discussed is that the algebra of the conserved charges can be obtained once we know the OPs of currents. And so in particular, if I have 2 charges, Q1 and Q2, so the commutator is just given, so this guy leads at Z1, this guy leads at Z2. So we can easily compute the commutator, and it's given by a contour integral of the phi dz2 over 2 pi I, and then we have a residue when Z1 goes to Z2, J1, Z1, J2 of Z2. And so we will make use of this stuff later today. Okay. So then we went ahead and we did a lot of examples. Actually, we discussed only 2 examples. So the ones that we talked about are the conserved charges associated with currents generated by the stress energy. So in other words, we use exactly the same notation. Yeah, so we looked at conserved charges, Jm, which would be defined Z1 plus 1, holomorphic plot of the stress energy tensor. And then the conserved charges are just Laurent coefficients of the expansion of the stress energy. So in particular, Lm equals an integral z by I, z to zn plus 1, z. And then what we did, we actually used the ideas of the OPs and related OPs to the commutators of Laurent coefficients, also known as Virasoro generators, and in this way we obtain Virasoro algebra. So the last thing, okay, not the last, but I guess the last before I started rushing too much. We discussed slightly that this whole idea can be extended to any operator. So if I have, you have to think of it this way. So suppose I have, suppose we have a primary field, primary field. Actually, I'm talking about holomorphic field. So this is an operator O. It depends on that only. So I'm going to assume that this guy has a holomorphic weight H and anti-holomorphic weight 0. So what we can do, we can represent this operator as a Laurent expansion. And the reason we can do it is that any holomorphic function has a Laurent expansion. Okay? So OM that M plus H. So this is just a generalization of Virasoro generators that would come from the stress energy tensor. If here we have T, and so the holomorphic weight for the holomorphic weight will be equal to 2. So in this sense, once you start computing the contour integrals, OMs behave as charges. Sort of similar to the Virasoro generators. And then we went ahead and we asked the question: what is the algebra of these charges with the Virasoro generators? And we derived a beautiful expression, which was actually easy to do because, again, all we need is this idea that the commutator of two charges is related to the OPs, and once we know the OPs, we could go ahead and do whatever computations we want. And so basically, yes, I'm missing some pieces. But I cannot reproduce. Okay. So in this way, we obtain the following algebra. Okay, so I'm not going to go to this derivation again. I'll just give you the answer. So this was M. M minus M. And what I want to emphasize is that this is a very, very general approach, and it works always whenever we're talking about holomorphic or anti-holomorphic operators. So what we would like to do now, so the purpose of today's lecture, and until kind of this will end our discussion of conformal field series, first of all, we have our favorite example of a CFT, the simplest CFT. So we look back, at X CFT, right? So the CFT of free scalar fields on the world shape. And then we will get, we will kind of develop these ideas, find out what are the corresponding charges when we do mode expansion of this field. And very important topic, kind of the main stuff I want to explain clearly today, is the idea that there is a relation between operators and states. So we talk about isomorphism between operators and states. So I'll try again to be general first, and then we'll go back and we'll look at this our point CFT to get some more detailed knowledge. All right, so good. So let's go ahead, and so what we ended up discussing is mode expansion, which is started for X CFT. So in this case, we have a bunch of free scalar fields. And even though the field itself, x mu, is not holomorphic or anti-holomorphic, del x mu is holomorphic. So it is holomorphic. And it's actually a conformal weight 1 comma 0. And so what we can do, we can do what I reminded you earlier today. We can write down a mode expansion in terms of Laurent coefficients. So there is some convenient normalization factor, minus I alpha prime over 2, and then I have sum minus plus infinity alpha and mu over z m plus 1, right? So this 1 is simply, again, reflection that we're dealing with a holomorphic field of weight 1. And we can do similar for the anti-holomorphic combination. So I have minus I on 2, 1 half, infinity plus infinity, therefore, n plus 1. Okay, and now that's really where we ended last time. So we will be asking the question, so are there any constraints that we have to impose on these Laurent coefficients to begin with? And so what we noticed that single valuedness of x mu of that block. So we want our Poisson field to be a single valued on the z plane. And so that implies, in particular, so what I can do, I can integrate these expressions, and the only problem can come up whenever we have logs, because log of that is not a single valued function on the complex plane. And so the only problem can come up from n equals 0 terms there. And so what you see once you do this integration of the two relations, you will find out that I have 1 half, and then we have alpha 0 mu plus z plus alpha 0 tilde mu plus. And so the only way when this expression plus single valid, and so the only way when this expression is single valid is when these logs get assembled into absolute value of log squared, which implies, so from this we concluded that alpha naught mu must be equal to alpha naught mu. Okay. So now we would like to go ahead and continue this discussion. In particular, we want to know, are there any other constraints that we would have to put on Laurent coefficient? And the answer is yes. Okay, so it doesn't go down somehow. So recall that when we studied various symmetries, so one of the symmetries we discussed was when our fields x mu got translated, okay, by a constant space-time vector a mu, and so there was a conserved current corresponding to this translational symmetry. And so this conserved current we derive is I del A x mu 1 over alpha prime. And so in particular, you can immediately see, well, of course, this current must be conserved because it corresponds to a specific symmetry. But we can see immediately that it conserves when I write it down, this expression in terms of holomorphic and anti-holomorphic indices. In this case, J becomes I over alpha prime del x mu, J mu, and then J tilde mu is I over alpha prime del bar of x mu, and del x and del bar correspondingly holomorphic and anti-holomorphic. So we know that whatever this world-shape current is, so the corresponding conserved charge must be the space-time energy momentum, right? So conserved charge corresponding to JA must be P mu, right? So what we can do now, we can actually see how can we express some of the coefficients in terms of the conserved charge. So our conserved charge, which we agreed with you, must be something that we should know by P mu. And on the worldsheet, what we have to do, we just have to compute this contour integral to get the conserved charge. Remember, that's what we always do, right? So we take a conserved current and we integrate it over a closed contour. And the fact that it's holomorphic, decomposes into holomorphic and anti-holomorphic plots implies that this contour integral does not depend on where we put this contour, okay? Which is again the reflection that this is a conserved charge. There's going to be that, and then there is a corresponding term coming from the anti-holomorphic plot by I. Right? So do I have to do this integral, guys? Or you can, there is an explicit expression for x, right? So I can compute that, well, for del's. I can just substitute it in there, right? Because I know also how the currents dependent, just a constant times del x. And so I evaluate these integrals using the recipes. Do I have to do that? No. By the way, we are falling very badly behind. I don't know why. I think it's good. Well, I mean, it's good and bad. The good means that hopefully you are asking questions and I go slow enough, and bad is that we end up learning a little bit less. But anyway, so you can do this arithmetic, and what you will find out, 1 over 2 alpha prime over 1 half. And so here I have alpha naught mu plus alpha naught tilde mu. And so those are the only terms that will contribute, which is again obvious because I need to look at the m equals 0 terms in order to have 1 over that singularity, which is something that will contribute to a residue. Okay. So we'll get this expression. Now we can use our condition that the single valueness implies that those Laurent coefficients must be the same. And so we see that actually these alpha naughts are related to the space-time energy momentum. In other words, P mu must be equal to 2 over alpha prime, alpha 1 half, alpha naught mu, and it is exactly the same. Okay, very good. So, so we have our Fourier, we have our Laurent coefficients, so those Laurent, again, I started by reminding you that you have to think about these Laurent coefficients because they show up as a result of a contour integral, right? And so as long as operator you are talking about is either holomorphic or anti-holomorphic, you have to think of them as conserved charges. And because they are conserved charges, then you can ask the question, what is the algebra, right? And so in other words, we can ask the question, what is the algebra of alpha and mu, alpha and tilde mu. Okay, and we know how to answer this question. Okay, so first of all, we kind of, from what we know so far, we have guessed that those coefficients must satisfy some kind of oscillator algebra. This is something that we discussed when we talked about electron quantization. But I want to emphasize that here we don't have to assume anything, right? So we know that those are our conserved charges, and then we can just follow our rule. How do we compute our commutators? Again, it was on the blackboard that I erased just before that. So Q1 and Q2 is going to be equal to an integral z2 over 2 pi I residue of z1 over z2, z1, z1, z2, z2. And so these conserved charges, alpha and mu, is just given by 2 over alpha prime, and the integral over z over 2 pi I, z to cm, well, that's mu, that. And so all we have to do is just, so our conserved charge, for example, J1, will be 2 over alpha prime, Z1 to Cm, del x mu of Z1. And so correspondingly for J2, so all we have to do is just take this expression, substitute it here, use the OPEs for the F system that we studied extensively, and evaluate the residues. And in this way, you will obtain the algebra of the coefficients in the mode expansion. So is it clear the steps that should be done, right? And those are very simple and straightforward. And unless somebody really wants it, I don't intend to do it here. So what we will find out, the following commutation directions. Is equals to and mu this is and mu. So if the mu is a space-time metric, and then we have x mu, p mu, which is I. Okay, so here I introduced x mu without explaining what it is. But in fact, once we know the expansion for the del x and del y, we can integrate this expression. And so what we will find out is going to be, there is a zero mode, so there is a constant which we call x mu. And then there is, remember there were alpha 0 and alpha tilde 0, which was multiplied by log absolute value squared. And we know that alpha 0 is expressed in terms of the space-time momentum. Let me just put this in. So, mu or that's where is plus 1 over 2 so I took out the m equals 0 term, right? So once I integrate m equals 0 term, I will get this log squared, and the rest will give me will be 1 over m alpha m mu over z m plus alpha m tilde divided by. Okay, Okay, so that what will come out once we integrate. So when we evaluate these commutation relations, those X mu is this zero mode here. Okay. So, so of course now once we have the algebra of the modes, we can construct a Fock space, right? So we can say that we have a vacuum. Okay, so this vacuum is going to be annihilated. Now this coefficients become an operators that act on our states. So what we can say that we construct vacuum by requiring that alpha n annihilates whenever n is positive, and then the vacuum is being annihilated by operator p mu. So we'll get 0 as well. Right, and so that's how we can think about the Hilbert space of the theory with these basic operators, the modes of the field acting. So we can get cyclic states by simply acting with raising operators. An excited state, and we can act with any number of raising oscillations.
So let's do the question. Why these operations enough to determine the vacuum state?
So again, this is my choice, right? So I see that actually up to a factor, they correspond to a bunch of decoupled, oscillator algebras. And so what I'm doing here, I'm constructing a Hilbert space exactly as you do for Hilbert space of a single harmonic oscillator, right? So I'm defining what I call my vacuum, and then I'm saying that I construct the states by acting on a vacuum with operators that don't annihilate it. So you might ask, what is special with this definition of the ground state? And that will come in a second, because we're going to ask the question, how does our Virasoro generators expressed in terms of these mode coefficients? And remember that L0 Virasoro coefficient corresponds to the energy in this omega frame, right? When we think about a CFT on an infinite cylinder. And so what we will find out that precisely this way of constructing a vacuum, defining a vacuum state. I should say that what I did here, I define what I call my vacuum state, would correspond to a state of lowest eigenvalue of L naught. So it's a natural way. Okay. So very good. It's a good question. So any other questions? Okay, so as I said, what we're going to do now is precisely this. So we're going to explore our states by actually asking how does Virasoro generators act on them? And to understand this, we have to express Virasoro generators Lm in terms of alpha m, right? And so correspondingly, the anti-holomorphic Virasoro generators will be expressed in terms of alpha tildes. So let me remind you that the holomorphic stress energy tensor up to a constant is just Lx mu. And let me also remind you that the way we define our Virasoro generators, so Lm, those were conserved charges defined in the following way. we have z, z m plus 1 t of z. So now, the point I want to make is that once I know the mode expansion for the axis, right? So we have an explicit expression. How does our x field is expanded in terms of Laurent coefficients of m? I can just plug this in and evaluate the contour integral to get an expression for the Virasoro generators in terms of Laurent coefficients. And so again, I'm going to skip the computational details. I'm just going to write down the answer. By the way, here, when I wrote the algebra up here, I wrote only a non-trivial commutation relation. So in particular, the commutation relation between alpha and alpha Twilio will always vanish, which is something you would expect because one corresponds to holomorphic sector, the other one to the anti-holomorphic. And in our theory, those two sectors don't talk to each other. Okay? So when you evaluate this integral, what we will find out is that Lm over line 1/2 m equals minus infinity to plus infinity. And then I have alpha m minus m mu alpha mu comma m. Okay, so the mu indices must be contracted. The reason for that is because notice that the mu indices are contracted here. So in the final formula, we try to have a contraction of mu indices as well. So why did I put this wiggly line? And the reason is that there might be a subtleties, right? So when I evaluate this, in other words, when I evaluate this integral, I think about alphas as being just C numbers, some constants, and so as a result, the order doesn't matter. On the other hand, we know that the mode coefficients alpha satisfy a non-trivial algebra, and so whatever order is will matter. And so this sign means that I'm careless about ordering, and so so this is something that we have to discuss. Okay? So what we have here, we ignored ordering operations. Okay, so yes.
I'm still confused by the notation. Do you mean Ln is equal to that?
Yes. So you can think of this as it's equal. Oh, right. So what I am summing. So this is Ln. Good. But again, this is an exact expression, and the only reason is that we have to worry about normal ordering. The point is that when n is not equal to 0, right? So the normal ordering, the ordering of those coefficients doesn't matter, because the only way when alphas do not commute, when m no, actually, sorry guys, this is the right thing. So it's n minus mn. The reason I have to switch back to m because otherwise there will be inconsistency with my notes. So I'm going to keep m here. Okay. So I'll put m here. I'm going to sum exactly as before, except that I switched M and N. Right? So the summation, I have Lm, the summation with respect to N, so I have N and N here, and there is M here. And the order must be different. Okay, so here I will have alpha M minus N. Okay, so so you can see that whenever N is not equal, whenever M is not equal to 0, then the index here plus the index here is not equal to 0, right? So I have, if I call this index M prime, and so this index M prime, then M prime is not equal to N prime, right? And now if you look at the alpha algebra, you can see that if those two indices are not the same, then the operator simply commute. So order doesn't matter. The ordering is not important. And so the issue arises only for m equal to 0. Okay, so let's see what we have then. Okay, so for L equals 0, I can write down alpha prime square 4 plus some n equals 1 to infinity. And then I have alpha mu n, okay, and plus ax. So this is a normal ordering constant. Okay, and so when I said that there is a specific normal ordering constant, which means that they have some specific order, and you can see that that's indeed the case. So here, first, what I have a conformal, what's known as conformal normal ordering. So I used conformal normal ordering. Right? So we already discussed before normal ordering, right? And that was the idea is that the reason why we wanted to do normal ordering of various operators, because then they will satisfy the classical equation of motion without any delta function in the free series. So here we have a different example of normal ordering. So what I have here, I have the annihilation states, right? So those are the states that annihilate vacuum. Note the summation goes only over the positive values of n. And the way we define our vacuum is by being annihilated by all alpha n. So here first annihilation operator. And so here what we have is a creation operator. And finally, so we have this normal ordering constant, right? So the first thing we want to ask is this normal ordering, is this a finite number? And the answer for it is yes, it is. The reason is recall that Virasoro algebra implies a very specific commutation relations for generators L sub m. And so we can use, and in fact, we derive the Virasoro algebra. All we have to do is to know the OPE of the stress energy tensor with itself, right? And we derive this Virasoro algebra for arbitrary central charge. We didn't have to stick with this toy model of free CFT. And so in particular, one of the things that we have in this Virasoro algebra is the following communication relation. So L1 is 1 when v equals to 0. So what I want to demonstrate to you is that once, given that we know the Virasoro algebra, and I will end up using this particular commutation relation, we will be able to unambiguously determine this nomological constant. Okay. So let's go ahead and see what's happening. So first of all, note again, we define vacuum in this way, but remember that previously we constructed our Hilbert space. By asking that Ln, when it acts in a vacuum, annihilates when n is positive. Well, again, vacuum doesn't carry any energy momentum. So now you can see that actually this condition is equivalent to the conditions that we use there. Okay. And the reason for that is whenever n is positive, then I have to use the expression for the Virasoro generator as given here. And so there will, in this product, there will be at least one alpha always which carries a positive index, right? So whenever n is positive, right? So when n is positive, there is no way to make both of those two indices negative, right? So if n is negative, and then this guy is positive. Now when n is 0, right, then this guy is positive because n is positive by assumption. And so there will always be at least one mode coefficient with a positive index, and so it must annihilate the vacuum. So the two vacua we defined today and previously, they're actually equivalent. Okay, and another what you can check as well. Well, first of all, the vacuum is annihilated by L1 simply because it carries coefficient positive index. But you can check that it's being annihilated by -1 as well. And you can see here that if I substitute -1 here, so I have -1 minus n, and so here I have n, and so again there is no way that there will always be one positive index. Okay, so given this, what we can do, we can act on our vacuum with an operator to L0, and we can use Virasoro algebra to write it down as 2 commutator L1, L-1, acting L0, right? So it's 2 L1, L-1 minus L-1 for 1 acting on 0, and we have just seen that L1 and L-1 will annihilate vacuum, so this combination is 0. Okay, so it must be true then. It must be true. True that L0 must annihilate the vacuum as well. Now you can see that L0 has 3 parts, right? So first there is square of the momentum operator. P acting on a vacuum will annihilate it, so this term will produce 0. So this guy is a normal product, which means that annihilation operator always comes first, so it will annihilate vacuum. And so L0 acting on a vacuum must be 0, but it's exactly the same as our normal ordering constant, A sub x, acting on a vacuum. And so from here, we can prove that AX equals to 0. So we have a finite and well-defined normal ordering constant. So, so you might be curious. Okay, so far we know two different types of normal ordering. So so there is this creation annihilation or conformal normal ordering, sorry. Well, there is this creation annihilation and the normal ordering that we used before. And the question is, we want to ask is there any relation between them? Okay. So let's go back. Let's look at a specific example of three fields. CFT. So I have my X fields, right? And so what we can do now, we can see what's the difference between two ways to do normal ordering by simply evaluating, right? So what we discussed before was the normal ordering in which we subtracted the singular part, right? So there was a subtraction there, and so in this case, the normal ordering was defined as following: have S nu bar, so it's a normal ordering. So this normal ordering here, the product of two operators satisfies the naive classical equation of motion, and then there was a subtraction u for absolute value squared. Actually, I slightly misled you. So this is creation annihilation of ordering, and this is just Forest guys. Okay? So the normal ordering that we used before, which I didn't call it this name, I just called it normal ordering. So now Polchinski decided to call it conformal normal ordering. So this is our old normal ordering, it's conformal. The ones that I discussed right now, creation and annihilation, is normal ordering that should have been called normal ordering without. That's the one familiar from quantum field theory. And this one is less familiar, and what I said is I reminded you how we defined it by requiring that the product of operators satisfies their classical equation of motion. However, what we can do now, we can ask, if I have these operators, I can do creation annihilation normal ordering, right? So I have an expansion for the fields in terms of alpha n's. So I can write it down as creation annihilation normal ordering. Okay. So here I use just simple dots here. Here I use empty circles to denote creation annihilation normal ordering. Well, in order to be specific, we can use this computation by assuming that absolute value of z is larger than absolute value of z prime. So I substitute the modes for the field x, and I have to do the the appropriate commutations, right? So I will always, I write the expression here, and now I want to do, I want to compute the coefficients alpha m in such a way that the annihilation operator stays first all the time. So when I do this computation relation, there will be leftover piece. And so this leftover piece, it's a little bit tedious, but it's very straightforward to do. So this leftover piece is just doesn't depend on the coefficient itself, right? So it just depends. On z. And so it is alpha prime over 2 eta mu minus log absolute value. So again, this is a very straightforward exercise. You substitute the expansion in terms of alphas here, in terms of alphas here. You rewrite, so the sum runs from minus infinity to plus infinity. You write down the sum that runs only with respect to a positive index, and you make sure that you use appropriate commutators. And so at the end of the day, you will get this piece. So so in this case, since we assume that absolute value of that is larger than that prime, so this sum is convergent, and we can evaluate this sum. In particular, what we can show that this sum is precisely minus alpha prime over 2 eta mu log z minus alpha prime squared. Okay. You can actually see the first piece, right? So when I do the expansion, I factor that, right? So here, the way I'm just telling you how you can check that this infinite sum corresponds to here. So what you can do, you can write this down, eta mu, and then I have log absolute value of z plus log absolute value z prime over z square. Here I have log value of z plus value And so now, under the assumptions that absolute value of z is larger, I can just do a Taylor series expansion here, and I can see that what I will get is precisely what's here. So the bottom line is that for a simple CFT, like the free scalar and free scalar CFT, the two types of normal orderings are the same. Normal So conformal normal ordering is the same as creation and iteration. Normal ordering. Okay. So you might think that, well, maybe if that's always the case, and the answer to that is no. So that's not always the case. So this relation is not always 2 is true. And so, so one of the things where we made a choice, so that it at least true in this case, is notice that we combine P mu with annihilation operator, right? It didn't have to be so. So we thought about P mu as an annihilation operator. So, and in particular, well, exactly where we did that, well, that was when we defined our vacuum in a way that's being initiated by P mu. Okay. Good. So, so any questions?
Yes. I think it's just a technical detail, but I want to know, there seems to be an inconsistency. So,
Sorry?
In this last expression, the second logarithm at the bottom,
Yeah.
shouldn't it be 1 minus z bar prime over z? Is that right?
That bar prime over z, that's correct. But here it's absolute value squared, right? So all I'm doing
I'm just looking compared to the previous expression, right? So you're factoring out a z. Right?
Yes.
And you'll have a z bar prime in the numerator.
That bar prime. Where do I have the bar prime?
That's
no,
the
I'm
first one.
factoring z, right?
Right.
Because I want to have this piece, right? So when I factor this, then I will have z, 1 z bar over z.
Z bar prime. That's what it. That's
Oh,
what's written.
sorry.
What's
Oh, no, sorry, it was right.
prime?
So
and
all
then-
I'm saying is that z minus z bar prime is z. There's no bar.
Okay.
Well, I mean, it must be, remember there, in the conformal normal ordering, right? So this is log absolute value of z. Z minus z prime.
Okay.
Yeah, so I just made it clear.
Okay. That's what it is.
So, sorry.
No. Good. I didn't know there were loads of things.
I'm a little bit slow. Okay, so very good. So, so let's move on. So let's do this exercise one more time, and let's do it for the BC system. One of the reasons is that I would like you to do some homework exercises on the CFT. And so one of them will be on this BC system. So let's just do this exercise here. We have the BC CFT. And so in general, we can now follow the same procedure. So here we concentrate on the holomorphic BC system. So our PLB is holomorphic. So it has a Moran expansion plus infinity. So I have Bm over Z m plus lambda. So C of Z is going to be equal to infinity plus infinity Cm Z m plus 1 minus lambda. So again, all I did here is substitute the weights. And so you might immediately start shouting at me saying, well, you know, this is not exactly the Laurent expansion because lambda can be something, right? So in particular, when lambda is fractional, then there will be branch cards, and so there are issues involved with that, and you're absolutely right. So in order to avoid this, so in particular, remember there was one very important case when lambda was fractional, right? So this is the case lambda equals 1/2, in which case the BC system simply described a pair of Wolff-Sheaf fermions, and it was important. I told you that it's important for the superstring, that's CFT. So, but what we are, so lambda is important. Superstring. And so it provides a fermionic counterpart of the bosonic wall sheet CFT. However, when we do our covariant quantization of a Polyakov string, the BC system that we end up discussing will be BC at lambda equals 2. And so in this case, for now, we're going to restrict our consideration to cases when lambda is integer. So when lambda is integer, then these expansions that I wrote are actually Laurent expansions, and so there is no nothing funny going on there. Okay, good. So we can go ahead and remember, first of all, our fields B and C, they anti-commute. So VC equals minus CB, and we also know the OP of B and C fields, B of Z1, C of Z2, 1 over Z1, 2. And so that's enough. That's enough to compute the algebra of Laurent coefficients Bm and Cn. And so again, we can go ahead. We can go ahead and repeat the analysis we did previously, except that before we talked about the commutator of two charges, right? So the commutator of two charges was given by this integral. I'm writing this at time today. Residue Z1 goes to Z2, K1 Z1, K2 Z2. And so in this case, because we have anti-commuting fields instead of a commutator, I will have an anti-commutator. So I denote this as a plus sign here. Okay. And the rest of the analysis go as before. And so once we do the computations, we will find out the following algebra. Okay. So the next step, as in the case of the XCFT, we have to go ahead and construct our Hilbert space. Right? So we will define the specific situation. So here, when m equals n equals 0, m equals n equals 0. What we have a one-dimensional Clifford algebra, right? So we have two operators with anti-commute, and so the representation of this algebra is two-dimensional. So in other words, the ground state is degenerate. And so what we're going to do, we're going to define the ground. We're going to define two ground states by denoting them as spin up and spin down state. Okay, and so those guys are defined as follows. So B naught annihilates the down state, and C naught annihilates the up state. Okay. V naught acting on an up state on a down state, and C naught acting on a down state on an up state. Okay, so that's the action of V naught and C naught on the ground state. And then similar to the X system, we're going to define that Vn acted on a down, Vn acted on an up, same as Cn up, same as Vn down equals to 0 whenever n is positive. Okay? So that's our vacuum. So now once we have mode expansion for the NC field, we can go ahead and write mode expansion for we can go ahead and evaluate expression for the Virasoro generators of this PC system in terms of modes for B and C. And so we will find out some n equals minus infinity to plus infinity, and then minus n. And then here I use again creation and iteration normal ordering. So I have Dn, C, n minus 1, plus delta m0 Hg. So again, I can repeat exactly the same words that unless n equals to 0, the ordering doesn't matter here because there will be at least one mode with a positive coefficient, and so it will annihilate the vacuum. It will actually annihilate both vacuum, and the only subtlety will come when m equals to 0. So in this case, they can be a normal ordering constant. So what we're going to do now, much like in the previous case, we would like to compute the value of this normal ordering constant. So notice that this is at least the second time we deal with normal ordering constants, right? So one is when we actually studied the string in the light cone quantization, and so there we use the regularization, something that you guys did also in the homework assignment, and you did a computation of this of some normal ordering constant, and you were unhappy, right? So that was somewhat dirty way of computing normal ordering constant, in particular because we have to sum up series which were infinite, we have to come up with regularization and all that stuff. And the physics wasn't very clear. So what I want you to take from these computations here, so we can all kind of fall through the cracks by being dragged in these technicalities. But the idea here is, again, so once you tell me that you have a CFT, it also means that you have a stress energy tensor, which means that you know the OP of the stress energy tensor with itself, which means that you know the Virasoro algebra with a specific central charge, and that so which means that you also have Virasoro generators, which means that these Virasoro generators have a well-defined have a well-defined algebra, and so using this knowledge, I can always unambiguously compute this normal ordering constant. Okay? So there is, that's if you wish, a physical way of evaluating normal ordering constants. Okay. So let's do this exercise here. So again, we're gonna use SL2R subalgebra of the universal algebra. So in particular, we're not gonna use the full SL2R subalgebra. We're gonna use again these commutation relations, which is insensitive to the central charge. And so what we're gonna do, we're gonna study the reaction of both sides of this identity, right, on the down state. Okay, so let's look L1 acted on the down state. Right. So this equals sum n equals to minus infinity to plus infinity, right? So I have to substitute m equals 1 and lambda minus n, and then I have a normal order where I have dn, and then I have c1 minus n, and it acts. We're supposed to act on the down state, right? So in this infinite sum, right? N goes from minus infinity to plus infinity. So when n is positive, right? Okay, so let's look first when n is negative. So when n is negative, you can see that I have a CMOM with a positive index, and so it will be annihilated, right? So then when n equals to 0, I have here a normal ordering of B naught C1, right? So I have B naught C1, and so this one is also 0, right? Because I have C1 with a positive index, right? But actually, you can see that well, when n gets positive, then Bn is annihilation operator. So I have to put it first, so it will annihilate as well. So this L1 will always annihilate the down like state. And so here I have L1, L minus 1, minus L minus 1, L1. So so when I act with this commutator on the down ground state, this term will not contribute. Okay? And so the only contribution will come from L1, L minus 1. L1, L minus 1. Ground state. This is the same as L1. And so you can see that the only contribution, the only thing that will not vanish in this infinite sum, that's n equal minus 1 term, right? So in this case, I will have B0 here, and this guy gives me this guy gives me B minus 1, and this guy gives me C0, but C0 does not annihilate the downstate, it flips it into an upstate. And so what I have here, I will have L1 acted on B minus 1, C0. Okay. So now remember that this L1, so it always has a coefficient that will annihilate the downstate, right? So what this means? This means that as I anti-commute L1 with B minus 1 C naught, I don't want any non-trivial coefficients to be left over, because if they are left over, then they will annihilate the state, right? So the only non-trivial piece coming from here will come from a combination which have a non-trivial anti-commutation relations with this B minus 1 C0. Is that clear? So if the anti-commutation relations is trivial, simply meaning that I just get a minus sign if I anti-commute. So this means that I'll be able to move some of the operators here active on the downstate. And so we just showed that if that is the case, then the downstate will be annihilated. And since we're looking for some non-zero x, if it is, then the only way it can come out from the term which must be C1 B0, right? And so in fact, you can see that there is a term of this type here. So I can write it down lambda B0 C1. So the reason why am I picking this up is because the only non-trivial commutation relation with the C naught is B naught, right? And the only non-trivial commutation relation with B minus 1 comes from C1. Right? So the only term in this infinite sum that will contribute is going to be n equals 0 term. Right? So I have B0 C1. So then B minus 1 C0 acted on minus 1. What I missed here is that the terms that we picked is n equals minus 1. So there is a factor here, minus lambda minus 1. So I have lambda, and then here there is a factor. Minus 1 minus that. Okay. Good. Let me write it down one more time. 1 minus lambda times lambda. B naught C1, B minus 1, not okay, so very good. I can anti-commute those guys, right? And so that will give me 1, right? Because afterwards I can add with C1 on this, so this becomes 1 minus lambda times lambda. You understand what I'm doing or not? Okay. What I'm saying is that I can replace this guy, so I know that C1 B minus 1 equals to 1, so C1 B minus 1 is equal to 1 minus B minus 1 C1. Right. So what I'm saying is that whenever I see C1 B minus 1, it will be 1 minus this combination. Now in this combination, I have C1, but C1 will always commute with C0. So I can anti-commute. So I can just anti-commute and it will initialize. So the result will be 0. So the only non-zero combination, the only non-zero contribution will come from this 1. So I replace this guy by 1. So I have 1 minus lambda lambda. And then I have B0, C0 acted on the downstate. And then you can see that the way we define C0, when it acts on the downstate, it flips the state up, and the B0 state flips it back. So this becomes 1 minus lambda acts the downstate. Okay. So now, by definition, it must be the same. It must be the same by definition. But so not by definition, by the Virasoro algebra, it must be the same as 2L0 acted on the downstate. Now the L0 contains the creation and annihilation normal ordering part, which will annihilate the ground state. And so the only contribution here comes from the normal ordering constant. Okay? So you can see now that unlike the FCFT, the normal ordering constant in this case is non-trivial. And so in fact, we just computed with you that AG equals 1/2. Again, all this analysis are very straightforward. You just have to be careful with commutation or anti-commutation. All right, guys. Any questions? No. Good. So now we kind of come to the last topic, and it's a very nice topic. So let's start with the question. That's a relation between operators. And so notice that all the operators that we studied, they were local operators, right? And so what I should say when I say relation between operators and states, what I mean actually by that is relation between local operators and states. And so once you understand this, then it becomes clear that there are several ways how you can think about the CFT. You can think algebraically that you have a Hilbert space and you have what we now call conserved charges. So it's Laurent coefficients of various holomorphic and anti-holomorphic operators acting on the Hilbert space. Or you can have the OPEs of operators. And what I want to explain now is that there is an isomorphism. So there is a detailed relation between these two concepts. Good. So we're going to talk about vertex operator. So what's the meaning of the vertex operator? Well, so vertex, you can think of vertex as being a state. So a vertex operator is an operator, a local operating in a CFT that would correspond to this particular state. Okay, so as I said, what we want to do, we would to build a map between states and local operators. In particular, one of the first things we want to understand is why is it possible? Why can we talk about local operators? And it will also be indirectly clear why do we talk about that only in the context of the CFT. Okay, so good. So remember that we talked about CFTs in two different languages, right? So two different frames. So one the frame was an infinite cylinder, right? So the time was imaginary omega, and so the circumference of the cylinder was space, right? So here, this was our sigma 2. So sigma 2 equals minus infinity. That's an infinite path. And that's where we want to prepare our state. So we prepare states here. Okay. And then let that state propagate and evolve, and whatever comes, whatever dynamics we have will take place. Now I can always ask a question. I can always act with charges on this state, right? So here I prepare the state, and so the state evolves in time. And I can ask the question, what if a charge Q acts on the state? So what I have to do, I just have to take a corresponding current and integrate it with respect to space. In our case, it's just a circle of circumference I, right? And so, a charge Q will be just a contour, it's just an integral over a surface of the cylinder. Okay, so this is an sort of charge acting on a state that we prepared at infinity. Right? So now, one of the beautiful properties of the conformal field theory is that it doesn't matter, in which frame we look at this theory, as long as those frames are related by holomorphic change of variables. And so, in particular, what we can do, we can go to the Z plane, and the correspondence is given by a holomorphic map that goes from that equals e to the minus I omega. So in this map, remember that prime runs radially, and the integrals over the space are just the integrals over the angular, over the angle of the Z plane. Okay. Then I want to remind you that omega is sigma 1 plus I sigma 2. And so we have periodically identified sigma 1 as a period. Okay? So we can ask, so this procedure that we did in the omega frame, right? So we prepared a state at minus infinity and we acted with it on a charge, with a charge Q. What does this mean in the Z plane? Well, so minus infinity, sigma 2 equals minus infinity. If I substitute sigma 2 equals minus infinity, you can see that Z approaches to 0, right? So the absolute value of Z. So let me say sigma 2 goes to minus infinity. That implies that absolute value of Z goes to 0. So the state that I prepared here actually get localized at the origin of the Z plane. And so that's why it's natural to think that there is a second local operator A that defined as the origin of the Z plane, right? So here I have a state A, right? And so now once I made this conformal transformation, I have a second local operator that is as the origin. And so the way, now this procedure, how do I compute a conserved charge acting on A? Well, in this picture, it's just become a contour integral. Right? In order to evaluate this contour integral, again, we can use residues in the structure of P's. So, this is a very general picture. And what we want to do now, we want to actually better understand it in much more detail. And so the ultimate goal here is, I want, at least in the simple example, like the free CFT, to show you that there is an indeed one-to-one map. You can go from this picture to the other one. For each of the state, you can assign an operator and do it backwards. Right? So any questions so far? So good. So what we want to do, we want to ask the following question. So suppose that our operator A, right, that's 0, 0 bar, it's just an identity, okay? And so we can ask the question, so what is the state that corresponds to the identity operator? This is identity operator. And so the question that we ask is, what is the corresponding state? Okay, so what is the corresponding state when we have an identity operator? Okay. So in this picture, what we can do in order to get an idea of what state we are talking about by acting on the state with a conserved charge. So I can choose whatever conserved charges I want to. And so I'm going to choose a conserved charge alpha m, right? So alpha m mu. So this alpha m mu, so I might be wrong by some normalization factors. So let me put it this way. So I want to evaluate the action of charge alpha and mu on a state corresponding to an identity operator. So in other words, I have to evaluate this contour integral. Right? I have dz over 2 pi I, and then I have that m L of x mu, right? So this is a conserved current. Corresponding to alpha and mu, right? Up to a constant, right? So there was a constant I times alpha prime over 2 square root, something like that. It doesn't matter. So it takes, this is a conserved current, and then I have to, the other operator that I have is 1, right? By assumption, we are asking the question, what will happen if I act with it, what is the state that corresponds to an identity operator? And so here, what I have to do, I have to, I don't have to evaluate, so this integral is going to be given by the residue, right? I can use the residue theorem to do this analysis. So the important thing is that when m is positive, right? So when m is positive, this combination here is non-singular, right? And so there will be no residue. So the integral is going to be equal to 0. So what we are finding that once we have an identity operator, so it corresponds to a state A such that alpha m mu acted on A must vanish for all m which are positive. Okay. But that's exactly how we define our vacuum, and so we have a relation that the vacuum corresponds to an identity state. Okay. Okay, so any questions? Yes.
This correspondence is just in CRT, but has a usual quantity theory. And automatic in this
Right. So notice that I would say that that's just a property of the CFT in which you can relate states to a local operator, right? Because in order to have this discussion, I have to have a local operator, right? And one way to have a local operator, I have to do this conformal map. Right? So I have to go from a cylinder to a plane. So the answer to your question is yes, it's in a conformal theory only. So there's this precise relation, and you will see that so for now we go kind of from asking the question, if you tell me what that operator A00 is, what is the state, right? And we try to guess what the state is by acting with different charges on that state and asking what's the action of this charge on the state, right? Much like we did there. But this property relation between states and operators is true also in higher dimensional CFTs. In particular, it's also true in superconformal gauge series. And the relation is kind of an extension of the map that we discussed here, which is the map between, if you wish, a cylinder. In this case, it was a cylinder and a plane. And so in the case of n equal 4 supersymmetric Young-Mills, which is a superconformal gauge theory, it will be a map between a gauge theory in 3+1 dimensional spacetime and the same gauge theory on a sphere. Right. So here, the space in which your two-dimensional conformal field theory lives is has compact space. Right? So the relation extends to high dimensional CFTs, but it doesn't extend at this level of precision to arbitrary quantum field series. Okay, so very good. So let's go ahead and continue asking this question. So now, so we know that identity corresponds to a vacuum. So we know that we can construct excited states, right? So we can construct excited states by acting with erasing operators on the vacuum. And so what this means that in the language there, we want to know what does this action corresponds to. So we want to compute the OPE. We want to compute the OPE of alpha minus mu with an identity operator. Okay. So this OPE will describe the local state A0, 0. Okay. So in here, I'm assuming this one is positive, and so in this case, what I have here, so I have 2 over alpha prime. I have a contour integral with respect to c, and we have z on 2 pi I. Okay, z that's mu. Okay, and equals so the contour integral will pick the residue. So I have to act with n-1 derivatives, right? Del x mu z. Okay, I have to do a Taylor series expansion of this holomorphic field, and so this is del x mu of 0 plus z 1 factorial del 2 x mu plus z n minus 1 over n minus 1 factorial, right? And then this is del m minus 1 on z on x. And so I have additional del here. So you can see this m minus 1 factorial comes from here. Then I have z m minus 1, and I have z to the minus 1. So I will have 1 over z. So the contrary integral will pick up just the residue. So I have, I will be left with del m x zero. So, so what we are finding is that alpha minus mu acted on the 0. So this state corresponds to the operator to alpha prime. Well, okay, so it's clear guys what I'm doing, right? No. Is it absolutely clear or absolutely not clear or in between? Why am I talking about okay? So if it is clear for you, who can explain me why am I talking about this? Why am I talking about conformal normal orderings? Yeah. What do I mean by that? Okay. Okay, if you don't say anything, then it means it's not. It means that you have stopped. So let's go back and look at this picture, right? So what do I have here, right? So here I have A, and here I have Q, right? So this Q is the guy that leaves, that is an integral, right, with respect to Z. So now what I want to do, I want to, so this guy is an integral of dz over 2 pi I, some conserved current, dz, right? So, so the important thing here is this current operator, right? So what I want to do, I want to rewrite this combination. I just want to evaluate this combination. So what I have to do, I have to compute the OPE of the current with A, and after that evaluate the contour integral, right? And so the answer is remember the way how we talk about conformal normal orderings, right, or OPEs. So I can just remind you this again. So if I have two operators, right? So O1 at Z, and there is O2 at 0, right? So what I want to do, so we started the operator product expansion of this of any operators in CFT. So I should be able to write this down as a sum, right? With some coefficients k, ck, right? And then I have, I have some some singularity 1 over z to some power, and then what I have here is normal, conformal normal ordering of operators, but they are evaluated at the same point. Okay, is that clear? So what am I doing here when I'm asking how does my charge act on operator at 0? I want to know what the operator, what will be the local operator left at the origin. And in order for me to evaluate what this local operator left at the origin, I have to compute this OPE, and after that I evaluate the Z integral, right? because what we're interested in how does the charge act as the operator at zero. So at the end of the day, Q acted on A00 must be some normal ordering product of local operators, which is situated at the origin. Okay? Is it clear what I just said? So let me repeat it again. So we have a CFT, right? So I have a charge acting on a localized operator. And so the charge is an integral of a current. And the way I can evaluate what's written here is by first evaluating the OPE, writing this as a set of local. So at the end of the day, there will be some operators, right? And I want to expand these operators in terms of operators which are located at the origin. So the way I can do this by evaluating the OPE, there will be a singular part of 1 over z, and then I perform the integral, right? So now I can perform the integral, say, around a unit circle. And so in this infinite sum, there will be only a particular piece that will come out. And so this particular piece that will come out, as you can see, is going to be localized at the origin, and that corresponds with the action of Q on the operator at the origin. Right? So that's exactly what we have done here, right? So so in particular, what I have been doing here. So I have alpha m, which acted on an identity operator. And effectively, what I was doing, if you think what I have been doing, I was trying to, so this guy, well, it's not really a good thing to write because this is a Laurent coefficient. It doesn't depend on that. But the corresponding charge depends on that. And so what I did, I was doing an OPE and integrating this OPE. So in fact, what I tried to do, I was performing this combination, right? So I was trying to obtain a non-singular part of the product of two operators, right? So that's exactly, in other words, this is another way of seeing how I can think about this, right? So there will be some singular pieces, right? In when Q acts on A, and I'm just extracting a non-singular piece, and a non-singular piece should be expressed in terms of conformal normal ordering.
Why the singular terms have not
Well, in this particular combination, you can see that the singular pieces will simply not contribute at all. So because the singular pieces will vanish, because what I'm acting with, I'm not acting with an arbitrary, operator. I'm acting with a charge, right? And which implies that I have to perform this quantum. So if I have 1 over z squared singularity in the OPE between current and operator, that will drop out of the integral.
that if I have
Right, and that's exactly what we've been picking up. Right? So that's when we are evaluating this integral, this piece that will be left over is precisely a 1 over z piece in the OPE of the current and the operator A. Okay. Okay, guys. So this is the most difficult thing to. It's a bit complicated thing to understand, but you would have to go back and think for yourself. Come say.
Just one more question. Yeah. So A is under the integral sign?
Sorry?
So
yes. So what I'm doing, I'm evaluating this Q that has a 0, 0. So and Q it can be complicated. So what I'm doing, well, strictly speaking, I'm having this, right? And now I want to write it down as QA, well, whatever, something, right? Something is a normal that is at 0, right? So now by that, if you think about this map, if I have an operator localized at the origin, that will correspond to a second state that I created at minus infinity. And so the operation, remember that the operations that we did here, so one way of thinking of this is that we can start with an identity operator, right? And we can act on, so this identity operator corresponded to a vacuum state, right? And then I acted with a creation operator, right? So this cube would be a creation operator. So then this operation here created me the first excited state, right? And so I'm asking, how do I think about this first excited state as an operator that is localized at the origin, right? And so this picture tells us that what we have to do, we just have to evaluate this combination, right? Where instead of this A, we substitute an identity operator. So that's exactly what they evaluated here. Now, to answer your question about higher singularities, of course, here you have to substitute the whole expansion, right? The whole well, I mean. So there will be more singular terms there as well, right? But the only one that is being picked up, which is one of the Z terms. This is the one. So it's del M, and it's evaluated at 0.
Another thing is now the partial X mu is Taylor expansion, but in the beginning, this class.
Right. So the Laurent, this is along the lines that I'm saying. Any Laurent term, because M is positive, what you end up doing, you end up computing an integral dz over z cubed with higher powers, and those integrals always vanish. Right. So that's what I keep saying, that in general there will be a more singular terms, but after you evaluate the integrals, they do not contribute. And you need to evaluate the integral because that's what you mean by this conserved charge, right? Okay. So good. So hopefully it becomes clear that this is the operator. This is the operator that corresponds to the first excited state. But in fact, what you can do, you can show this in general, right? So suppose I have some state, A, right? And so I want to act on this state with minus alpha m minus alpha m, sorry, alpha minus m mu, right? So it's going to be equal to, I need to know the normalization, otherwise I will not know. It's going to be confusing anyway, and if I'm faulty, then it will be even worse, right? So, so this will produce a new state, right? A new state, and I want to know what this new state is going to be. So, in order for me to answer this question, I need to evaluate. The pictures there. So alpha minus mu is just 2 over alpha prime, which is a common one. Is over 2 pi z to the n x mu. So here, this is just alpha minus mu. And so this guy is these at point z, and so here I have a corresponding operator that is located at the origin. So what we have to do, we just have to evaluate this integral, right? So so one way you might worry is that there can be singular terms. So first of all, so this is alpha minus m. So I have to act with minus m here. Right, and so what I want to say is that, well, you see, you can say, look, I have. But first of all, is it clear that this state will correspond to this combination? Do you all agree with that? Okay, because the only question is to evaluate this number, right? So, so in principle, there can be this A can be a complicated operator, right? And so when I look at OPE of X and A, there can be lots of singularities, right? So and the singularities will come up when I do a cross contraction. So this guy can contain X, right, at 0, right? Or some complicated derivatives acted on this axis. So what I have to do, I have to actually, when I use this Taylor series expansion, I can either Taylor series expand this, right? I don't have to worry about negative terms in the Laurent expansion, right? Simply because, well, I mean, they will not contribute. But I also don't have to worry about cross contractions. The reason is that whenever I do this cross contraction, remember that the cross contraction will bring down a log of absolute value of z. Okay, that will be a cross contraction if I cross contract x from here and x from here, right? But what you see is that I'm actually contracting del x, so there will always be a derivative, at least one derivative, acting on this log. Absolute value z squared, right? There can be more derivatives. For example, if what is sitting here, there is del x of 0, 0, then actually in this cross contraction there will be minus the other derivative. So it will be minus del 2 acted on log z squared. The important point is that from cross contractions, what you get here, you will get at least 1 over z. Right? Because if you add with a single holomorphic derivative, you already have 1 over z. So if there are more derivatives, you will get higher negative powers. So what this implies that when you are evaluating this contour integral, you already have z to the minus m, and m is positive. So you are actually increasing the negative power. So you are talking about, so this integral, if you look at the terms that come from cross contractions, then the only terms that will contribute are the terms, well, so there will be terms of this type. So it will be m plus 1 at least, right, or larger, and m is positive. And so this integral simply vanishes. Okay, it's a contour integral. The only integral that doesn't vanish is dz divided by z, but you already have, m being positive. So this number is larger than 1. So these contour integrals will vanish. Okay, so the only non-trivial piece that can come from this integral when we do Taylor series expansion of del x mu, right? And it can come up precisely as we did up there, right? So it can come up only from. So now, so I know that there will be nothing interesting coming up from cross contractions, and I can simply put now simply put the conformal normal ordering, right? Because conformal normal ordering takes care of the singularities in between the cross contractions. And I just argued that cross contractions cannot contribute to this integral. So now what I have this holomorphic expression, and it can just Taylor series expand. And so when I do Taylor series expansion, then this is what I wrote before. So this is going to be del x mu of 0 plus z divided by 1 factorial del 2 of x mu of 0 plus del m z del m x of 0, right? Z exponent n minus 1 divided n minus 1 factorial, right? And so now you can see that the term that I wrote up here is actually the only non-zero term that will contribute to the integral. Because I have z to the n minus 1, and so here I have z to the minus m, so I will be left with the integral dz over z. So in other words, so you can evaluate the integral, right? And so so what you will find is that this new state is going to be equal simply a normal ordering, right? The reason why normal ordering is because here in the product we went back to a normal ordering, and so the only term that will be left. Okay, so first of all there will be a bunch of constants. So 1 half I over n minus 1 factorial. And then inside the normal ordering, so we have to do Taylor series expansion, and we will be left with simply del m x mu of 0 in of 0 from 0 bar. Okay. So in other words, now you know for sure that so there is this local operator that corresponds to the creation operator alpha minus n mu. And so I can write down schematically acting on some operator. So this is simply the same as a normal order of alpha and mu acting on A. Right? I just simply put the corresponding creation operator inside the normal. Very good. So I'm going to ask the question again. So is this clear what they did? So let's do the following thing. So you will think over, and next time I'm happy to answer your question. So this is an important aspect to understand. How do we construct local operators from states? Okay. So let's take a 5-minute break now, and so we will continue. And what I want to do now, I want to go. I will give one more example. And then we will go the other way around. So we will ask the question. Okay, so this is very nice. So there is a state, and you use the conformal map to produce an operator. How to go the other way around? So, for example, if you give me an operator, local operator at the origin, how do I produce the state? Right. So, what is the state? How to compute it explicitly? And so we'll do this after the break. Okay.